Yes.
Well, many thanks for your presentation. And now, any questions, comments, criticisms? Yes, Professor Albert.
Hello, Silvio. Very interesting, as usual, presentation. Very interesting things that you showed to us. But again, I have always the same curiosity about how you were able to detect and identify, for example, the quasi-periodicity. How you do that in your numerical setup, and how do you identify those changes? Because sometimes they are very subtle, right?
Yeah, I see. I agree with you. That's something social. And yeah, I use Lyapunov sponge. So for both cases, you got one that's completely zero because associated with the time for the periodic perturbation, for periodic excitation. So there's no problem. There's another one that's is a kind of oscillation between around zero. So you have to use Lyapunov sponge, and for a long time to be sure to, that you have a quasi-periodic solution. And after that, I check the solutions. I use different condition conditions. I follow the attractor. I mean, there's different approach to check if you have a quasi-periodic solution or not. For example, I showed the torus that come from a stroboscopic map. So that's an indication you have a quasi-periodic solution. But there's something else. There's, for example, if you use instead of excitation with just one frequency, I use two frequencies. Another kind of problem you can face, like strange attractor, a non-chaotic strange attractor. In that case, it's quite difficult to know if you really have a strange attractor with no chaotic. Yes, it's not easy. Anyway.
More questions, more comments, suggestions? Professor Mario, please.
Oh, yes. I have a question. When you see the torus doubling as you change a parameter, is there any universal property as a constant, such as in the Feigenbaum root? I mean, is there any relation between the parameters that you can identify?
Yes, that's a really good question. In this case, it was not easy to identify the Feigenbaum constant. So, but I'm looking for that. But I believe so. I believe so. I believe that's possible.
Thank you.
Appreciate.
More questions, suggestions, comments? No. Then many thanks again, Professor Silvio. Thanks for accepting for our presentation. Good.
Thank you very much, guys.
And now our next speaker, invited speaker, Dr. Eduardo Brugnago. Eduardo, are you here? Are you here? Can you hear me, Eduardo? Okay, Eduardo, start to connect your microphone now.
Hello?
Are you hearing me? Yes, yes.
Oh,
I can hear you. I have two dispositifs here. One for I listen, another so I speak. Sorry. Okay. New technology. My voice have echoes. Yes. Yes.
yes.
So, and now? Now, okay. And now, are you hearing me? Yes, yes. Now is no echo. It's perfect now. Please, could you share your presentation? Yes, yes. Could you share now? I can't. I can't. The voice is perfect. Here, I don't capable to share my presentation because I have a message. Do you need to? Ah, okay. Right. Can you see my presentation? Yes. Uh-huh. Uh-huh. Okay. Okay. And now Dr. Eduardo Bugnano from Curitiba, Paraná. He has a postdoc position, a supervisor, Professor Marcos. Sorry, I was muted. Oh, Eduardo. And now our next speaker, Dr. Eduardo from Curitiba. He has a postdoc position, and the supervisor is Professor Marcos Barnes. I can see your presentation, Eduardo. Feel free to start. Many thanks. Nice. Thank you very much. Thank you for the opportunity to present my work. And today I will talk about some techniques, some strategies of feedback control based in synchronization suppression strategies based on feedback control applied to neural network. It's interesting to study because synchronization, the synchronized activity of neurons is related to motor problems, epilepsy, and another neuronal problems. And we don't into deep in the medical questions, but just model a very simple neural network and consider three different feedback control suppression strategies, always based on the mean field of the activity of the neural network and apply it in three different ways, as we can see. First, we need abstract neural network because the structure of the brain is very complex. So the first abstraction that we can think is a graph model. So we transform the neuronal network, the real neuronal network, in a graph model. And from this graph model, we can obtain conclusions about the techniques that we can return to the real network. So our modeling approach considers the location of the neurons. So the soma at each node. So each node of the graph represents a neuron. In really the sum of the body of the neuron is located in each node of the graph, and the synapses, electrical or chemical synapses, are represented by the edges of the graph. So we can the brain can present electrical synapses that's bidirectional, represented by green edges here, and chemical synapses that are directed and represented by black edges here. So if you have this structure, we can now represent the neuronal network by means of its adjacent matrix and model each vertex, so each node of this graph as a dynamical system. This dynamical system models the activity of an isolated neuron. So first we start from a high complex structure and model like a graph, locate the neurons in each node, attribute synapses, electrical or chemical, according to the edges of this network, and model each node as each neuron as a dynamical system. So in this work, so the three results of the works that we present here, we consider Rukov neurons because we are not interested specifically in the activity of the neuron, but we are interested in the synchronization of the activity. So we can suppress the synchronization. And the Rukov neuron is very fast to simulate, and we can obtain great results that can be transposed to continuous time or more realistic models. So here we consider Rukov neurons, specifically in the burst regime. And to compound the network, we include two coupling terms. The first one, C index E, is the term of electrical connections, and the C index C is the term of the chemical connections. And these two terms have this respectively strange. So if the strange of chemical connections epsilon C is equals to 0, we does not have chemical connections in the considered network, that it's not realistic, of course. And if epsilon E is 0, we have no electrical connections. So in the human brain, we have in turn around the 10 or 20% of electric connections, and in some simulations we can make epsilon E equals to 0, but not epsilon C equals to 0. Remember that the chemical connections, the last term in this expression, is unidirectional, and electrical connections is bidirectional. So these terms is opened in these ways. Electrical connection is bidirectional, and we consider an straight to normalize key E is the total of electrical connections in each neuron of the network, and GC is the total of chemical connections in the respective neuron in each network. So we normalize both for the total of connections in each neuron, and see that the chemical connections depends on a threshold theta to effectivities, to this effectivity. So H is the Hepside function. So if xn is greater than theta, we have an spike, and this connection is established. So the connection can be of two kinds. The connection can be excitatory or inhibitory, and it is modeled by this term, P. And M is the total adjacency matrix of the system. Delta term is a chronic delta that gives us one diagonal, main diagonal of the adjacency matrix that gives us the internal connections into each subnetwork, because as we can see here, we have two super indexes in X. It signifies that we have some networks, and each network have some neurons. So we have 1, 2, 3, 4 P index to network and U index to the neuron in each network. And once established the connection, we obtain our network, in this case, a cluster of networks, and each subnetwork in this cluster represents a cortical area in the human brain, as you can model following. The single neuron activity, as I say, is in burst regime. So I can see in black the single neuron activity, and in red the mean field. So the mean field in each network, when the activity, the neuronal activity in each network is synchronized, we have the mean field accompanying the bursts of each single neuron, but it's not occur when the activity is not synchronized. In A panel, we have the synchronized sample, and in B panel, a sample of non-synchronized. Of course, I represent just the activity of one neuron in both, but the red line is the mean field. So it's important because the mean field is directly related to the activity, to the synchronized activity, and it is the information that you use to employ with feedback control. And we consider the feedback control in three different strategies. The first strategy is the delayed mean field triggering. So we consider a delay in mean field, so the expression to add the feedback control is it. So epsilon if is the strength of feedback control, and G of capital X is the function of the mean field that effectively employ the control. So in the first strategy, we consider the delayed mean field triggering. So this triggering signifies that we can on and off this actuation, the G, according to the Hepside function, if the X is greater or lower than a certain threshold. The second strategy is the three-stage switch control. So the first is two stages, and the second one, the second feedback control strategy, consider a three-stage switch control. So we can make nothing with the network, but we can insert an stimulus to find, or inserting a suppression signal to find, and it's acting in different neurons in different forms, because the synchronization is in the synchronization of network occurs in the burst region, but the individual firing in each burst not is synchronized. So if we stimulate the first neuron of the first network to fire, it can not stimulate a fire to the second neuron in the same network, because it is in different states, but also in the burst regime. So bursts synchronized, not necessarily firing into bursts synchronized. So in the third strategy is the floor delayed mean field. So the mean field does not acting like an one-off switch, but is incremented according to the floor function that implement perturbation that is greater than the last integer most close to the mean field value. The mean field is in reals and the floor is in the integers. So we can see how it's operating and the results that we can obtain with this. In the first strategy, we consider the delayed mean field trigger. So the network that we operate this strategy is composed according to a human connecton. In here, first picture, we have just an illustration of a schematic illustration of the network. So we have a cluster of networks or a network of networks that is given that this connection is given according to a human connecton, but each network that represents each cortical area is given by a scale-free network represented in this panel with blue background. So the scale-free network has a hub and another secondary hubs that we can perturbate a single hub, we can perturbate a percentile of the network, or I can perturbate all neurons in the network. It's important to see that we consider a special cult in the universe of possible networks. What I can see. So we does not have neurons or subnetworks that acting a sink or a font. What it means. So for each two pair of neurons in a subnetwork, we have a patch that lead from the I neuron to J neuron. We guarantee it by means of an algorithm that we developed a few years ago, named Roman road. So we can obtain a patch from each pair of neurons. It's important because if we have subnetworks that acting a sink of signals, of acting like font of signals, we is unable to affect this network from the signals applied to the neurons outside the subnetwork. It's in the case of the font. In the case of the sinks, if we disturbate acting the control in the only the neurons into the subnetwork that act as sync, this signal does not propagate to the network, to the global network. So we guarantee that don't have this behavior in our simulations. So again, for each pair of neurons I and J, we have a patch from I to J. And we also consider the networks without autopsies. So we don't have a eigenconnection, and we does not consider for chemical synapses, we discard the loops of the one step. So what's the loops of one step? If neuron 1 is chemically connected with neuron 2, where neuron 1 send signal to neuron 2, neuron 2 does not is chemically connected to neuron 1 in this direction from 2 to 1. So if you have the connection from I to G, chemical connection, we don't have a chemical connection from G to Y. This is also important because we does not obtain premature synchronization. So in this first work, we obtain with moderate levels of epsilon, and here we consider just chemical connections, and we have a high levels of synchronization in all subnetworks and the global synchronization. The variation of the synchronization of each subnetwork in the simulation is in Salmon range, and the global synchronization, this R is the order parameter, the Kuramoto order parameter. This blue curve indicates the synchronization level of the global network, and the mean of synchronization of each subnetwork is given by is represented by the red line. So we can see that with epsilon equals to 0.1, we have a high level of synchronization, and for greater values 2, so high synchronization is R close to 1. So to apply the suppression, we include a suppression term like we show here, and we can a metric to evaluate the succession of the suppression. So we consider the variance of the mean field, the relation of the variance of mean field, that's a suppression metric, and we need S greater than 1, very greater than 1, to obtain high adequate levels of the suppression, like we can see. So this control.
Hi, Eduardo. Just one second.
Beta, and given by a head side of the mean field in each subnetwork with a threshold theta. So we can see that S, the suppression measure, close to 1 is not good because we does not suppress the synchronization, and S close to 1000 to greater than 10 and closing to 90, we have good results in green. So from black to cyan, not good results, and from red past to yellow to green, we have good results. In the first panel, we fix epsilon, the chemical strength parameter, equals to 0.1, and we vary the delay in the measurement of the mean field and the intensity of the beta. The intensity of the beta is the strength of feedback control. To calculate the suppression levels. So for beta greater than 0.02, we have greater values of suppression greater than 18. So for all delayed values, and the highlighted box in the panel B is the sum of the highlighted box in panel C, where we vary in panel B in the vertical line the delay value, and we fix the delay value in panel C and vary the strength of chemical coupling to obtain the relation of the strength of chemical coupling and the intensity, the strength of the feedback control necessary to obtain good suppression values. So, in general, for beta equals to 0.04 for all evaluated values of chemical coupling strength, we have very good suppression values. What signifies? It signifies, the green region signifies that we obtain a good suppression of the synchronization. So the network does not more synchronize behavior. So when S is equals to, when S is equals to 1, we stay, when S is equals to 1, we stay in this scenario, in the panel A scenario. When S is greater than 10, is close to 100, we stay in this scenario, and we and it is the desirable scenario because we suppress the synchronization, the synchronized activity. So,
Eduardo,
in the next
can you hear
work,
me?
we consider a three-stage switch control.
No.
But we does not apply it in the sum network of the previous behavior. We consider here also a network of networks. We consider also the cortical connections according to the human connectome. The B panel here is a representation of the cortical connection matrix. So when we have in black the zero level, we don't have the connection from the area, the cortical area T to cortical area D, and we have few connections in blue, and we have two cortical areas highly connected in red. So, of course, we don't have just 6 cortical areas. It's a schematic representation. We have 7 to 8 cortical areas, like in this work. So sorry, we does not show the matrix here, but some matrix presented here. So in this work, each cortical area is represented, is simulated by a scale-free network. But here we does not have a Barabat-Albert scale-free network, but this network is growth according to the Bianconi-Barabasi algorithm. So with this, we obtain a network with very much hubs. That is important because in this work we are interested to apply the perturbation just in the emitting hubs. So according we fix the chemical connections in the work. We fix the electrical connections and vary the chemical connections, like you can see in the panel B of the two right panels, and representing this panel in color code the intensity of the synchronization internal in each subnetwork. So red is very synchronized and blue is low synchronized or not synchronized network. So considering a value epsilon chemical epsilon C equals to 0.1, we have the panel A, where you can see the global synchronization in blue and the most of the subnetworks in a synchronization level greater the global synchronization. A few of the subnetworks in small values of synchronization. So we can now apply the three-stage switch control that consists of 3 levels of control. So if the mean field in each subnetwork is smaller than a threshold, we apply an stimulus. If it's into 2 values, we don't act in the subnetwork. And if the mean field is greater than a second threshold, we employ stimulus in the sense to suppress, to an inhibitory stimulus to make the activity of neuronal activity down. So we does not intend to apply this control in all neurons of the network. So in the previous work, we apply this function in all neurons. So in the case of three-stage switch control, we does not intend to apply this control in all neurons of each subnetwork. We choose to emitting hubs. What means emitting hubs? Emitting hubs is the neurons that have most connections starting from there. So an emitting hub is a hub of emission. So it's emitting signal for other neurons in the subnetwork. So we consider here internal connections only. So when we apply the control only in 5 emitting hubs, we don't have satisfactory synchronization suppression levels. But when we apply in 10, 15, or 20 emitting hubs, we have a very satisfactory suppression level. And it's important to say that the delay considered to apply the three-stage switch control needs to be small. So if the measurement of the mean field is time passed, very time passed, the measurement, the switch control is not effective. So to compare, we consider the 20 non-emitting hubs because we can make a question. So the effectiveness of the three-stage switch control is for applying it to emitting hubs or not, or it's is sufficient to apply it on 20 randomically chosen neurons in each subnetwork. The answer is that it's necessary to apply it in emitting hubs. So we can act on few elements of network only if that these elements is the emitting hubs of the network. So as you can see in this additional panel, we can suppress in the panel B, most right panel B, we can apply to the 20 emitting hubs in each cortical area, we can obtain very low values of synchronization. So here we show the order parameter, the Kuramoto ordered parameter in color code. So cyan is a very low level, and for the intensity of the epsilon feedback fixed as 0.1, we also obtain high levels of suppression, which correspond to low levels of synchronization indicated by the ordering parameter of Kuramoto. So we can see that the strength of feedback is important because to epsilon feedback lower than 0.08, we don't obtain the suppression of synchronization. So these results show here is for epsilon feedback equals to 0.1. So the G function is multiplied by epsilon f in this equation here. So epsilon f in the case of two-station control must be almost 0.08. And the last case is the floor delayed mean field. This control is in this form. Here we consider just chemical connection, different of the previous case. And the floor delayed mean field signifies that we apply the for function that gives us the greater integer smaller than x, or x is or equals to, is a real number. X is a mean field with tau delayed. And when we apply this function with all the neurons of the network, it's not an advantage. So the best result is considered the two-stage switch control because it acts on a few elements of the network, but the result is here is very interesting because also considering a human connecton when we start
Hello, Eduardo.
the control in the 3000
hello, Eduardo. Can you hear me? Hello.
From it, the magenta background, we can see for different values of epsilon feedback, that means the different strengths of control.
Hello, Eduardo.
Fast control. So in very short time, we reduce the order parameter, the Kuramoto order parameter in special case of epsilon feedback equals to 0.05. So it's important to see that the three-stage switch control, it's necessary that epsilon feedback is greater than 0.08, but acting in only 20 emitting hubs is sufficient to suppress the synchronization of the network. In this case, we need to acting in all neurons of the network, but the level of the strength of the perturbation is low than the previous case. We can obtain satisfactory suppression of the synchronization in with epsilon, or the strength of epsilon feedback equals 0.05. So the synchronization levels with small epsilon feedback values in each subnetwork. So in each cortical area, B panel, the right from the two pair of the right panels, the B panel, is very right. But when epsilon feedback is greater than 0.02, the synchronization falls abruptly, and it is sufficient to control the synchronization in this network with this strategy. So we have an advantage with the three-stage switch control that is acting on few elements of the network, and the other hand, the advantage of the floor delayed mean field is the law strength of the action in each subnetwork. So that's all. I open to questions. Thank you very much for your attention.
Oh, hello. Hi, Eduardo. Can you hear me? Eduardo. Eduardo. Can you hear me, Eduardo?
Wait.
No. Now, can you hear me now? Eduardo.
Seu volume está um pouco baixo. Deixa eu ver aqui se é aqui.
Hello, Eduardo.
Espera aí, vou fazer uma coisa aqui. Vamos ver.
If possible, you could turn on your camera, your cam. Hello, Eduardo.
Oi, teu volume está um pouco baixo ainda. Deixa eu ver se consigo aumentar aqui.
Hello, hello.
Acho que vou dar um jeito.
Eduardo, can you hear? Hello, câmbio, Eduardo.
Alô, agora, tá ouvindo?
Hello. Yes,
Hello?
I can hear.
Okay.
Can you hear me? Okay.
Yeah.
Eduardo, if possible, you could turn on your cam. No.
Connection down? Oh, here. Hear me?
Turn on your cam, please, if possible.
A moment, please. So I am using my smartphone, so I can start using the cam.
But are you listening? Yes?
Yes, I listen.
And now we have a problem with the cam, but any question, any comment, any suggestions, criticism? Eduardo, okay?
Hello? Okay. I listen.
Yes, your cam is possible turn on or no?
So I'm using my smartphone, and the site can. So it's asking for webcam. It's not webcam, smartphone.
But no problem.
I can configure it here. Does not start sharing because it's fine for webcam.
That's okay, no problem. You have a short time now. Then any question, comments? My question was about your camera. You respond me. And now, no question, no comments. Thanks again, Eduardo. Many thanks for accepting. For all, many thanks for attention. Many thanks for your participation. Okay. And the time now. Many thanks for our time dedicated for watching the presentations. And thanks, Professor Silvio. Thanks, Eduardo. Thanks for all. And now, Professor Albert, comment, suggestion, next schedule.
No, that's okay. Thanks so much, Professor Batista. I think you can finish the session if nobody has any further question.
Okay, and now finish your section. Good weekend, and until the next presentations.
Bye-bye.
Bye.
Bye bye.
Bye.
Bye bye.